In the last video concerning operational amplifiers, I promised you guys that we were going to do kind of a correlation between the non-ideal operational amplifier and then the ideal operational amplifier. We're going to kind of see through working through practice problem 5.1 in the book, we're going to actually go through and show how the ideal operational amplifier is actually derived. And kind of the principles that exist behind it. And also why we use it basically to really gain a good understanding of operational amplifier circuitry. So in this problem, we basically have a non-inverting operational amplifier. We saw in the previous video that the gain that we got on the output actually inverted that polarity. In this case, because Vs is connected to the positive terminal, then we're not actually going to see that inversion of polarity on the output. But a couple of things here. Well, here we want to actually find the closed loop gain of V naught over Vs based off what we would actually see across the 20k ohm resistor. And so here on the negative terminal, we got connected to a 5k ohm resistor and a 40k ohm resistor. And those are actually connected to, well, the 40k ohm resistor is connected to 20k ohms. So what we're going to do is replace the operational amplifier with its equivalent model and then once again solve everything with nodal analysis. And then we're actually going to go through and resolve the problem on conditions that we have derived from looking at the non-ideal amplifier and then utilizing the ideal op amp. So if we replace the operational amplifier, we basically have its internal resistance here, 2 mega ohms, very, very high, in which Vd is negative to positive. And then we also have on the right-hand side of that, connected to ground, is basically our dependent source of the open loop gain times Vd, and then connected to 50 ohms. And so basically everything that's in red is essentially that non-ideal operational amplifier model. So one thing I want to make note of, because I think this may confuse students, is would this internal model here change based off the fact that we have basically Vs connected to the positive? Why wouldn't some things in here flip? And I've heard this question before. And in terms of where everything's connected, and that's not the case. What really matters is the fact that Vs is now connected to where we would actually see is the negative terminal of Vd. So what we're going to see is that the positive terminal is tied down to a different node, and that's actually going to drive the non-inverting aspect to hold true. So in looking at this, to solve this with nodal analysis, one thing that I want to make clear is that AVD is actually tied down to ground, which actually ground exists down here. So because of that notion, it'd be better to just go ahead and redraw the circuit, and that way we can actually just get a better visualization of it. And so what I did was, because this node right here that we saw from the original circuit is V naught, we're actually going to go ahead and take this and we're going to rearrange this right side portion of the operational amplifier's model. We're going to pull it down to here and connect AVD down to ground, just to kind of give us a better visual. And sure enough, everything on the left here stays the same, especially with the internal resistance here. But now we have that dependent source of AVD connected to the 50 ohm resistor that's connected to V naught, and AVD is tied down to ground just as we would expect it to be with the operational amplifier's model. So I went ahead and just assigned our currents in here because we're going to solve with nodal analysis aspects. And so here I1 is coming to node V1 that I've just labeled, and then we have I2 coming out of V1, and then I3 is coming out of V1. But for over here, we're going to have I5 going into V naught and then leaving V naught as I4 through the 20k ohm resistor. So a couple of things that I want to go ahead and note, because we're going to be utilizing this later on, is that let's go ahead and just relate based off I1 how we can rewrite Vs and V1 in terms of Vd. So the voltage that's across this guy right here. Negative to positive is considered VD across the 2 mega ohm resistors. So Vs minus V1 is actually equal to negative VD based off the polarity that we actually see across that 2 mega ohm resistor. So sure enough, if we rewrite this, then VD is equal to V1 minus Vs. So we're going to come back, and just like we did in the original problem, we're going to go back and substitute that in. But first, let's go ahead and just write out our KCL equations and then expand those by, obviously the current voltage characteristics, and then just go ahead and start solving for basically the closed loop gain of what we would actually find is V naught over Vs. So let's take a look. Now this is where you guys should be looking at this going, oh God, this is what we got to do for electronics, analog electronics from here on out. The answer is no. And, well, it's pretty messy if you just first inspection. It looks pretty dang messy. Just like we saw in the prior video, we either had really, really large numbers or really, really small numbers. And so we're actually going to see that to be very, very consistent with this problem as well. But we're actually going to take some notions out of this, and we're going to derive basically the form of the conditions that we would actually see for the ideal operational amplifier. And once we get to the ideal operational amplifier, we're not going to be doing any of this anymore. This is going to be gone. We're just going to utilize the model of the ideal operational amplifier and go from there. It's going to make our lives with solving these types of circuitries very, very, very simplistic. So what we're actually going to see too is essentially we're going to break down our analysis down to basically one line, essentially, compared to all this right here. So let's just go ahead, brute force method, let's knock it out. Come on. Node V1's I1 is equal to I2 plus I3. Let's go ahead and expand that. Vs minus V1 over 2 million, 2 mega ohms. That's a, we'll come back to that. That's equal to V1 over 5,000 plus V1 minus V out over 40,000. So rearranging the problem, multiplying through by 2 million just to go ahead and get that out of the denominator, we get Vs minus V1 is equal to 400 V1 plus 50 V1 minus 50 V out. We go ahead and just rearrange that equation because we know we're going to have to allow it to equal to 0 in order to basically go back and perform, just substitution so that we can actually get everything in terms of V out as well as Vs. Here we get 0 is equal to negative Vs plus 450 V1 minus 50 V out. We're going to call that equation 1 right here. And going back to what I said, we don't have to allow this to equal to 0. We could have kept Vs on that side. It'd be totally fine anyway. Either way works. Because we're going to be combining like variables in the end, right? All right. So that's our equation 1. Ugh. Let's look at node V out. I3 plus I5 is equal to I4. V1 minus V out by 40,000, just like as we said before. Here we got AVD minus V out divided by 50. Oh, that's another variable in here. That's going to equal to V out over 20,000. Let's go ahead and substitute in the open loop gain A, and then also what we have is VD that we saw on the left-hand side over here, where we rewrote VD in terms of V1 and Vs. So rewriting this equation right here, okay, rewriting this equation, we get V1 minus V out over 40,000 plus 200,000 times V1 minus Vs minus V out over 50. And that's equal to V out over 20,000. So if I go ahead and start multiplying both sides by 40,000, and then go ahead and take into account everything in the denominator, and this term right here basically being divided by 50, we get some big numbers, guys, and also relatively small numbers. We get over on this side, we get V1 minus V out plus 160 million times V1 minus 160 million times Vs minus 800 times V out, and that's equal to 2 times V out. Well, these guys don't really matter. V1 and V out, V1 minus V out and then 2V out over here. No, we don't even need to worry about those. I don't even care about those numbers, essentially. We got 160 million right here, and then 800. Let's just go ahead and just not even worry about those. We're just going to X those out, heck with it. And we're just going to care about this section right here. So V1 is equal to 160 million times Vs plus 800 times V out. We're going to divide that by 160 million. And essentially, that comes out to be equal to Vs plus 0.000005 times V naught. And I'm going to say that that is equation 2. In fact, actually, it almost would suffice to say we could just leave that out. And if we go ahead and substitute 2 into 1 down here, guys, then what we end up getting is negative Vs plus 451 times Vs plus 0.000005 times V naught minus 50 V naught. And when we do that and just basically rearrange everything, and in fact, actually, I just went ahead and just left that guy out because it doesn't matter. That's so ridiculously small, who cares? Then we get 450 times Vs, and that's equal to 50 times V out. So in that case, V out divided by Vs is actually equal to 9. So that's our gain, is a factor of 9. And not only is it just a factor of 9, it actually also shows that by connecting Vs to the positive terminal of the operational amplifier, that we actually do not perform an inversion in terms of polarity. We actually keep the same polarity as we do on the input, so V out over Vs is equal to 9. All right, it's pretty messy, right? Let's see if we can come up with a couple of things here. Let's see if we can come up with an understanding. From what I can tell from this mess right here, is that if we look right here with V1 is equal to, all that is equal to Vs plus 0.00005 V naught. In fact, actually, it would suffice to say that V1 is actually just equal to Vs. So it means that essentially by this derivation, at each input, whether it's the positive or negative, by this non-ideal model here, we actually derived that essentially V1 is actually equal to Vs, meaning that the voltage at both terminals is actually the same. Okay? V1 is equal to Vs. A couple of other things. What about the current through that internal resistance? It's so dang high. Vs minus V1 right here, divided by 2 million? I don't know why my voice just went up that high. I would suffice to say that, number one, if Vs minus V1 is equal to 0 anyway, because they're the same, even if there was some voltage that would exist, divided by 2 million, that's just doesn't matter what their voltages are, because that current's basically going to be 0. So the current between the two nodes through that resistance is actually equal to 0. So what that would actually mean is that any current going to both of the inputs have to be 0 as well. So the currents going to the inputs of the negative and positive terminal have to both be equal to 0, and also the fact that these have been derived through an approximation of V1 is actually equal to Vs. These two concepts of the currents at the input being 0 and also the voltages actually being the same allows us to derive a new model that takes away the need to even go through and look at all this analysis through essentially nodal techniques. We don't have to do this. We literally just derived the ideal operational amplifier. Let's not even worry about this anymore. It's gone. It's gone. Let's take a look at something new. Well, just as I said before, guys, the ideal operational amplifier based off what we took a look at over here, I1 was equal to Vs minus V1 over 2 million. That's equal to basically 0 amps. So that means that the internal resistance is not equal to 0. It's actually equal to infinity. And also, by this approximation here, as I said before, it basically renders the fact that V1 is equal to Vs. So the ideal operational amplifier here means that I1 and I2 both are equal to 0 amps at the input. And V1 is equal to V2. So let's go back to the original problem. Practice problem 5.1. We're going to revisit that now with the ideal operational amplifier. We're going to solve for that closed loop gain. Now, that closed loop gain, here that means if we just go ahead and look at the circuit, see, we don't even have to redraw it anymore. We don't have to redraw it with the internal model. Here, we can easily see that at the negative terminal, Vs is just going to be that value here. And then also, I0's leaving, and then we got V out, and then we got a simple circuit here that we can easily analyze with quick KCL. Just quick KCL. If we wanted to actually find out what that current would be based off whatever value of Vs, then here we would actually say I0 is equal to I1 plus I2, which is equal to V out over 20,000 plus V out minus Vs over 40,000. But how would we know what V out is if we don't know that gain? So let's actually prove really quick that what we found through nodal analysis on the left over here, we actually could easily find that gain very, very quickly. And whatever Vs is going to be multiplied by that gain on the output. We could easily go through here and find that current very, very, very simplistically. So at node Vs right here, I2 is equal to I1, right? I2 is equal to I1. So, sorry, I2 is equal to I3. Sorry, guys. So I2 is equal to I3. V out minus Vs over 40,000 is equal to Vs over 5,000. If we go ahead and rearrange this equation really quickly, V out over Vs is equal to 9. Guys, check this. This is awesome. That closed loop gain we found in essentially 1 to 2 lines of calculation versus everything that we had to do over here with nodal techniques and substitution in order to actually find that gain. That gain exists right here, and we actually derive that gain up front. We derive that gain up front, and then we derive the concepts that allow us to go ahead and just analyze this circuit right here with simple, just ideal approximations to the fact that the two currents at the input are equal to 0 and that V1 and V2 are the same. And so from here on out, we're not worried about that non-ideal stuff. No, we're not going to worry about that. We're just going to utilize the ideal operational amplifier and just motor through the rest of Chapter 5 just to show some examples of the different types of ways that we can actually utilize the operational amplifier to perform specific functions. And that should set you guys up just fine for analog electronics over at UTC. And then you guys can keep rolling and doing great things. See you later.